Welcome to Insight Builder channel and an interesting video on introducing Accelerate and PEFT to democratize large language models. Training and inference of big large language models with less hardware resources. So the challenge that we are talking about is inference with less. The first challenge most of you guys must have already faced is that working with large language models can be little bit intensive. So why I mean to say this? Because you need GPUs, that is graphical processing units, for loading these large language models and getting it to even provide you the generations. So if you guys are totally new to all these aspects, and if you have not come across any of these large language models and artificial intelligence models till now, so you must have already come across various applications of artificial intelligence. You must have used various chat GPT plugins. You must have worked with chat GPT, the browser tool. What we are going to discuss here is to actually go behind the scenes of these applications and these tools and see how the large language models really tick, means how they really work. I have a series of videos and playlist in my YouTube channel. Do take a look at that, which especially dives deep into such concepts of how the large language models are fine-tuned, how the large language models are working as open source in Hugging Face Hub. And I in fact have an entire playlist where I discuss about Hugging Face Hub open source models. Do take a look at that particular playlist inside this YouTube channel. With that said, let me go back to the presentation. Before we move further, I would suggest that you guys better, if you have not got the Hugging Face Hub account, do sign up for Hugging Face Hub account. There are lots of things that you can achieve with Hugging Face Hub, and out of that learning artificial intelligence and large language model training using transformers and PyTorch is only one task that you can achieve, but there are various other benefits of working with Hugging Face Hub. So do sign up and use the hub for your benefit. Now moving forward, let us first of all understand. So you have a large language model, you have come across some new model. Say for an example, you came across OPT model, or you came across an MPT model, which is 7 billion parameters, and once you try to load it, even whether you are trying it in Google Colab or you are trying with Kaggle, you immediately find out that the system, I mean the Kaggle instance or the Google Colab instance, immediately crashes. And the reason is it could be multiple reasons, and the most frequent reason that I faced personally is that the model size is bigger than the RAM size. So this is something that I realized pretty late as I was working with large language models, and I realized that this could be an issue that you guys also might be facing. So what I mean that the model is larger than the random access memory, and why it is important. So for that, let me go to the browser again and let us go to the Hugging Face Hub. So if you go to Hugging Face Hub, there will be lots of models available. So you have to just look for if you go to, okay, let me actually show you that also. You guys might be new. If you guys are not new, just fast forward a little bit, so where I'll be starting to discuss about GPTJ. So if you go into tasks, and if you go scroll down, you will see natural language processing tasks, and in that, if you go into text generation, that's very important. We are talking about large language models with which generate texts. And once you go down there, you will see that there are at this moment they are talking about Falcon 7 billion instruct model that is kept for a demo here. And if you scroll down, there will be lots of other models that you can take a look at. So Bloom 560 million, Big Code, Star Coder. So there are lots of models available. And the moment you go into the model, so once you go into the model directory or the model page, you'll see the model card, and you'll also look at the files and the versions. So if you click on the files and the versions, it will show you the various files that is available inside which supports the model, like the actual PyTorch or Flax or TensorFlow file, bin file, and along with that, you will see the size here. So you see the size of this GPT 6 billion is 24.2 GB, which means even on a NVIDIA 24 GB GPU, this will not set. So you might be wondering, Kamal, why it will not sit in NVIDIA 24 GB GPU? Because when you are working with NVIDIA or any of the GPUs, the CUDA software, the software that runs all this models underneath, that particular software itself or that particular programming language itself has to load its own kernels, its own platform, so that you guys can start using the GPU. So that itself takes around 2 to 4 GB of space inside the GPU. So it's quite a huge application. With that said, so this particular model will not load in 24 GB GPU also. So you might need 2 GPUs, that is 24 GB, or you might need something of 16 GB, 2 T4 GPUs. So you need to work with some kind of an alternate option to load this model. And even then, there is one more challenge you'll face. So if I go to Collab Notebook, so let me go to this Collab Notebook, and if you click on this, and you'll see that the system RAM that is provided by default is 12.7 GB. And inside this 12.7 GB, you cannot make 24.2 GB to set. If you try it, automatically the system will collapse. I mean, it will say that the system is out of RAM and the instance will collapse. So now you guys might be thinking, okay, Kamal, I've never come across such an issue. So why would I ever think about these things? Okay, today, as we are talking, the large language models are still at the beginning stages of taking over most of our activities. So as the days progresses, the large language models slowly will start pervading into our daily activities. What I mean to say, daily activities. So there are lots of things which we do it through programming now, which will be slowly getting automated, and instead of using programming, we can start using these large language models. So you will be seeing why I'm telling this in a couple of minutes when I introduce PEFT, that is parameter efficient fine tuning. So at that time, you will actually start facing this challenge that model is unable to load. So you might actually walk through some of the tutorials somewhere, and then they will ask you to load the model. They will have a different GPU capacity, and you will have a different GPU capacity. And if you are trying to load it, it will not load. So how to work around this? So this particular couple of slides, I will be explaining that particular aspect. So when the model was small, so it was in the range of 7 GB to 12 GB, that is during the time of BERT and Roberta, when the transformer models were evolving. At that time, when the parameters were in millions, not in even 1 billion was not crossed. At that time itself, the model parameters were in 7 to 12 GB of space. So at that time, the entire model can be loaded into memory along with the weights. So the model itself has got an architecture, and on top of the architecture, there are parameters, and these parameters are by default instantiated as floats. That is FP32 or FP or TF32. So whichever version you are using, that itself will actually, the empty model, the model that is not trained itself becomes very huge. I mean, it actually takes space. After that, once you load the model into the memory, once you start training it, so again, when you are going to train it or when you are going to create an inference, the model is going to be copied and it is going to be loaded into the GPU. So it's going to be copied. So there is going to be 2 copies of the model and 1 copy is going to be deleted. So the model, whichever model you are talking about, is going to get loaded into the RAM, and then it moves to the GPU or to any location which you are asking it to move. And then only you can start the inference. So this is going to be a challenge for you guys, because if you're going to talk about anything in above 7 billion or even 7 billion parameters, the model is going to be huge. So as you saw, even in case of 6 billion GPTJ, it was going up to 24.2 GB. Yeah, there are certain ways of quantization. I had discussed about 8-bit quantization. You can work with the bits and bytes library and 8-bit quantization or 4-bit quantization, and also there is normal float 4-bit quantization. I'll be showing you that also. the point here is that, okay, quantization is a very different way of compressing the model. Here, what we are talking about is actually using the model as it is, but dividing the model into multiple pieces and loading it in different locations inside your own system or your server. And for doing this, the library called as Accelerate has been created by open source community, and it has been kept inside the Hugging Face Hub for your usage. So what happens when Accelerate is used for loading the model? So first and foremost, an empty model is created. How an empty model will get created, I'll be showing it in a couple of minutes. So there is something called as init wait empty waits. This is a method that is a part of Accelerate library, which can be used. Second, the device map. Device map. There is something called as a device map configuration that we can provide, and we can also have a kind of a default device maps like auto, balanced, low, and sequential. When it comes to auto, meaning it will try to allocate as much memory as possible on all the devices. When it comes to balanced, what will happen is it will start working. It will start working from the so balanced and auto are very similar now. So they will allocate equal memories on all the devices, whether it is disk, whether it is RAM, whether it is GPU. It will allocate equally on all the devices. When it comes to balanced low 0, so it will allocate less amount of memory in GPU 1. If you are having multiple GPUs, then the first GPU will have less memory allocated, and then the rest of the GPUs will be filled. In case of sequential, it is opposite to balanced low 0. So all the first to the end of the GPU will get filled, and the last GPU will be having lesser memory allocated. So when I say what is memory allocation and how these models gets loaded, we'll be seeing it in a couple of examples in next few minutes. So stay tuned for that. And so here you see that first of all the model gets loaded, and it actually is a skeleton model that is sitting there, and we bring the weights from the checkpoint. So the checkpoint is something that we showed here. Reconnect. Checkpoint is something that I showed here. So this is the checkpoint location, and we can ask the model to load from these checkpoints, and then it will go and sit inside the weights. But when it is going to get loaded into the weights, already the model itself has been segregated into multiple parts, and it has been moved to various locations inside your system. So when the checkpoints are getting loaded, it is going to be loaded according to where the model skeleton has been segregated. So you will see this in action in a couple of minutes in the next slide. The point here is all these things we are doing only for doing the inference. It will not be able to do training like this. So training the model that is segregated like this or separated is going to be a nightmare. So people are working on it, but it will be very, very extremely slow, because if you are going to work with model that is located in the disk, in the RAM, in the GPU, you know how much amount of the communications has to happen between these devices. It's going to be very, very difficult. So this particular YouTube video actually shows a very good introduction about what happens in these steps. So what I have done here is basically whatever I explained in the last slide, I have just listed it down here. And also the process only supports inference. The model layers needs to be together. So there are certain things you need to take care. As I already explained, how the models weights and location of the weights are decided, how the models can be sharded, how the model layers needs to be allocated. So all these things we will be looking at in the next step. First, one of the couple of limitations. The limitation here is at least one GPU is required. You cannot do any of these things just using CPU. It's not going to work. Memory management with Python is going to be a nightmare. So what happens is the model, once it gets loaded into using the Python related objects, Python has a tendency to hold the memory and it does not release it. Unlike PyTorch, it actually releases the memory once it is not required, but it's not the case with Python. So it could be a bit of a challenge. Disk offloading is also one of the options which can be slow. Also the model parallelism, if you are going to use model parallelism. So you guys might be completely new and you may not know any of these things. So the idea is not for you guys to to understand all this nitty-gritty details of what is going on. All I want you guys to understand is that even if the model is big, there is a way to load it inside your system. This is what I want you guys to primarily understand, and rest of the things are different. So if someone says that okay, the model cannot be loaded, ensure that they have done the research and ask them the relevant questions, so that you can be sure that okay, they are really saying that the model cannot be loaded. Currently there are a couple of models which are not supported by Accelerate, so you can take a look at that details in this particular location. Okay, it seems that I have made a mistake here. The Accelerate supports all the models currently that is available in Transformers, also as well as available in Hugging Face Hub. But if you're going to work with a completely different kind of architecture that is not linked with the PyTorch and with Transformers, then probably there will be surprising results. But as of now, there is no any issue with any of the models getting loaded using Accelerate. So you can get the details in this particular page. I have given these information in the necessary, if you go back to the PDF, I have also shared the reference links, so you can take a look at that. Now, steps in Accelerate. So what exactly happens? As I explained, so first an empty model skeleton is loaded, so it gets loaded into the CPU RAM. So this is CPU RAM. And the model is actually located here. The model is empty, as you can see here, and GPU is also empty. The second step is here. So the model is loaded into the memory. So the model checkpoint gets loaded into the memory of a single shard. So the memory that we are having has to be sufficient to take at least a single shard, or else it's not gonna work. Once the memory is loaded into the single shard, and based on the configuration, the memory maps or the device maps I was talking about can be used, and then based on that, the parameters that was loaded can be loaded into the model. So it goes into the memory first, and then it goes into the model. So before it actually goes into the GPU or goes into the model, what happens is Accelerate keeps a kind of a checkpoint. So you see this kind of a reference mark, that square. So it goes and actually understands at each layer or each level of the model and where it is located inside the GPU. So this first part of the model is located in this location of the CPU. So that is moved to the GPU, and then it goes to the second. So this one goes back, and then the second one comes and sits here. So if you see the video, you will take a look at that. But I wanted this particular set of slides to be in a single location. I attribute all this details to the author of this particular video. So this particular video, I have just taken a snapshot of that video and I have shared it to you guys here, so that you guys can actually understand it as a overview. Rather than taking a look at the video, I just want you guys to look at it in a single slide. So yeah, the video is much more informative also, and this is how Accelerate works. So, and what we are going to do next is we are going to go, as usual, I always talk about creating practice locations where you can work with the ideas that I'm sharing. So Collab Notebook is what we will be using, and I'll be sharing you the code that I took it from the internet again, from the Accelerate library itself. I believe that you like this video. Do leave a like and share it with others, and also subscribe to my channel for further updates on similar kind of libraries in artificial intelligence, large language models, and Python ecosystem. Let us go to the browser. But before that, so here, as I was already telling, this particular process is only for inference, meaning you can actually load the model and you can use that model to generate text. You cannot train it at this moment. You can do training, you can work on training it, but I mean, even the library says that you can train it, but it will be very cumbersome and it will take a lot of time. So with that said, let us go back to the browser and let us get on with the with this particular notebook. So this particular notebook, I was working with bits and bytes 4-bit integration. Initially, I was talking about, I was thinking about creating a video that discusses about the 4-bit quantization. And recently, I have been making a couple of videos on the 4-bit on the quantization aspect of the models. And if you come to this particular playlist, that is Mastering NLP with Hugging Face Up, and if you go down, I have a deep explanation on the quantization process here. So 8-bit quantization. And I was when I was thinking of making a 4-bit quantization video, I was not finding the necessary level of content to talk about. So then I felt, okay, let us talk about accelerate, bits and bytes, as well as PEFT in the single video. So as a bonus, in this video I'll be talking about bits and bytes also, but I will not be going really deep into that. You guys can take a look at it. So it's an important library, I'm not denying that. However, the things that you can learn from bits and bytes and quantization, you can learn it from this video also. So I would suggest that take a look at this video. Now, going back to this particular discussion, so this was actually the file that was shared by Hugging Face Up and Bits and Bytes, and it was part of the Lora process, that is quantized Lora paper. What they do is, Lora is low-ranking adapter configuration that I will be talking when it comes to PEFT. So let us not go into bits and bytes for this particular part of the video. Let us go to it later. So just hold on for that couple of minutes. Here you see I am pulling in bits and bytes, pulling in transformers, PEFT as well as accelerate. So I am getting all the necessary libraries and I am getting it from their GitHub repo directly to get the maximum updated, the latest updated library, and I am installing it. Here is something different. So here I am trying to clone into this particular sharded GPT. So you see this sharded GPT is having 7 GB of one file and 5.2 GB of another file. Both of these combined together is almost 12 GB. So this sharded GPT model is kind of a scaled down version of this GPT 6 billion original model. And we are going to work with that particular sharded model in a couple of minutes. So I will show you how. What happens is, we first of all start by working with the Eleuther AI GPT 6 billion only. So we are going to use that model only, but we are going to only get the configuration of the model. So you see, we are going only use auto config, not the auto model or auto tokenizer here. We are going to use only auto config. This will get the configuration or the skeleton of the model. Next, what we are going to do is, we are going to initialize the empty weights. So when I raise this particular call from config, so it will refer to this config file and it will create the empty model of GPT J6 billion. So the architecture of the model is more important nowadays. Depending on the transformer architecture the model owners or the model researchers have used, the output will be different. So I'm not going to dive into that aspect of creating the actual neural networks. It is something which is a little bit lower in the abstraction, or I should say it is a little bit higher in the abstraction complexity, because you have to enter into PyTorch, you have to understand how the neural networks are, how the various parts of neural networks are created. I would really urge you guys to take a look at PyTorch and learn that. But before that, if you can understand these things, then learning PyTorch will be much more easier. For me at least, it has been easier because I understand the overall picture. Then as I dive into the details of individual libraries or individual parts of the puzzle, it becomes easier rather than coming up from the details, because details takes a lot of time to master. Like if you have to master PyTorch, it is going to take at least 3 months. But if you have to master working with large language models, it's going to take less than 3 weeks, because it's more about loading the model. It's more about working with various libraries, various classes. So practice time is limited. But in case of PyTorch, it's going to be longer and more involved. Oh, okay, so that is a digression that I went in. Now the empty model has been initiated, and I'm going to use something called as tie weights. After that, this is where the actual fun starts. So there is something called as load checkpoint and dispatch, which will actually get the model from this particular location, because once I use this git clone, it is going to place this model inside my directory here. Okay, and then I can locate the directory and I can start loading the model. So I am using device map equal to auto, and also as I told that if the model is unable to sit inside this particular instance of RAM and GPU and CPU, it will be offloaded to the disk. And so let me try this. Let me actually, yeah, this is already GPU enabled, so I can actually go ahead and run this things. Let me run that, and it is going to take a little bit of a time, which we have already got, so should not be a problem. And if I run all these things, I'm going to show you a couple of things, and then we will go to the next step. So let it run. It will take a little bit of a time, and let me see what is happening. So it is still installing the library, so it's going to take a little bit of time. So let this happen. So I've given you the brief of it, and now I'm going to go back to the PDF. I'm going to save a little bit of time and go into the next step of introducing PEFT. So I have right now spoken about inference, and I'll be showing you the example in a couple of minutes. But what about training? What if you want to train a simple model, a T5 base model, which is 220 million parameters, or if you want to go a little bit larger, go for the 3 billion range models, and if you want to train it, is that possible? Okay, so you can actually load, after you load the model into the GPU or into your RAM, the training, the fine-tuning process can be equally complex. So what I mean to say is, there are multiple ways to do the fine tuning. So you can actually tune the entire model, that is entire 3 billion, 7 billion, or 176 billion if it is going to be OPT model. All this can be done, but it is going to take a huge amount of resource, and it is going to require you a lot of GPUs, and it's not going to be really easy. But what if I said that you can only fine tune certain part of the parameters, not the complete all the billion parameters, maybe in millions or less than a million. So what will you think? And if you are new to this, all this, large language models, this may not make any sense. So what does the billion parameters has to do with large language model accuracy or large language model efficiency? Okay, so this is one point I want you guys to take. The larger the number of parameters, the better the model is able to learn the task. So I will repeat again, larger the number of parameters, the model is able to learn the tasks, that is natural language processing tasks or vision tasks or audio tasks better. That is one of the identification most of the NLP practitioners are having. Now, instead of actually working with all the parameters inside the model, PEFT, that is parameter efficient fine tuning concept, comes and gives a couple of other options. So they say instead of actually fine tuning all the parameters, we fine tune only part of the parameters. So instead of fine tuning a billion, we only fine tune 1% or 2% of it. And one of the benefits, a couple of benefits, is that the new checkpoints that is getting created are very small in size. So assume that if you are going to work with the entire 7 billion or 6 billion parameters, it is going to take equal amount of space in creating the new checkpoint. But if you are going to only work with part of the billion parameters, say 1 million, then it is going to take very less amount of space. So you'll be seeing this in action. So train the new tasks and save that model is going to take you less amount of space, and at the same time you are going to get the full benefit of the model. Also, there is something called as catastrophic forgetting. There's a concept where if you are going to fine tune a model that's a big model, and if you are going to fine tune it with new data, it has a tendency to forget its old training. This can be avoided when you are going to use parameter efficient fine tuning. Third, the benefit is that when you are going to deploy multiple tasks. So if you want to do classification, if you want to do text generation, if you want to do some other task, and if you want to have each model as a separate instance, then it is going to take huge amount of space. But if you're going to use parameter efficient fine tuning, this is going to take very less amount of space. So let us just hold on for a moment there, and let us go to the browser for a moment. Let us see what is happening. So right now we are seeing that the model is getting the model is getting downloaded right now, and it is getting cloned. And next what will happen is it will get loaded into, we'll start working on this slide, this particular cell. So we still have time. So let us go back to the presentation. I mean, this is one of the benefits of programming. So once you understand it, the system will do whatever you want, and in parallel you can do other things. So as I was talking about the benefits of parameter efficient fine tuning, next what we are going to do is what kind of ideas or what kind of things are required for working on parameter efficient fine tuning. So parameter efficient fine tuning comes with a couple of strategies. So there is a separate library itself. It's called as parameter efficient fine tuning PEFT library, and it is also hosted in Hugging Face Hub. You can take a look at that. I'll be also showing it. The process integrates, so as I was telling, it integrates with Accelerate. It also integrates with Transformers library, and it also brings with SOTA models. Not all the models, couple of models. So PFT can be used with text, video, and audio modalities. All the three modalities can be supported. So I have told two methods here because the prefix tuning and prompt tuning are very similar. So that's why I have told two methods. One is Lora and another is prefix and prompt tuning. In case of Lora, that is low ranking adapters, the models, say for an example, if you take GPT 6 billion, so let us go back to the browser. So yeah, I think here the model has been completed, and so here the model loading has been completed, the model weight has been tied, and you see here the model is getting loaded into the GPU. So you see the RAM got used and the RAM fell down and the GPU started getting loaded. And this particular aspect of, you see the GPU climbed up right now. So the model moved the things from RAM to the GPU. After it moves, then the RAM will fall down. So once the actual activity is done, then you can do the inference from this particular model. So you saw the RAM is falling down. This is what I was talking about. And this level of understanding is very important if you are going to start working with the large language models, and if you are going to use it in production, and if you are going to, especially if you are in DevOps or if you are in MLOps, you guys must be already aware of these things. I needn't tell you this, but if you are into DevOps, probably you might be new to these concepts of machine learning models and what they do, how do they work, how the things move from the RAM to the GPU to the disk. So you see here the model has been loading from 20 GB to almost 50 GB. So 25 GB of data is already here. So what is happening? Let me go here and let me show you something. So there is something called as offloader folder. So this particular offloader folder will contain the parts of the model which did not get loaded into the CPU, into the GPU. So as I was explaining, GPU also takes couple of does not allow all the space available inside the GPU for you to load the model. If it is a 16 GB RAM or a 15 GB GPU RAM, it will have at least 1 to 2 GB of CUDA kernels. So it will not let you to load all the, it will not let you to take all the space. So you see, this is the various other parts of the model that is loaded onto the disk here. So this is what I was talking about. So understanding to this level is key for you guys to really work with large language models. And especially if you're going to push it to production, if you're going to work with, improving the throughput of the model, improving the throughput in the sense, improving the inference, improving the overall customer way of thinking. So that time you will need to understand these things. And so I have tried basic inference here. So you don't need to worry about this. This is just an introduction that I was trying to provide, so you guys can understand this. And you see here, I am also facing an error here. This is happening because the model that I downloaded here did not download properly. So this is a problem that I am facing in Colab, but in your system it will not be the case. Okay, so this is something that I was talking about, Accelerate. So I was moving around between PEFT and Accelerate library. So to save time, I hope that you guys can actually see the difference. Now let us go back to the PDF again. Just to recap, let me go back. So I was talking about this process in Accelerate. So you saw how the model empty weights got initiated, how the checkpoint got loaded, how the model moved from the checkpoint to the CPU and then to GPU. So you saw all this process in the Colab notebook, and I was talking about Accelerate library, right? Let us continue with PEFT right now. So I was talking about the couple of methods that you can use parameter efficient fine tuning, and among them Lora is one of the methods. It is called as low ranking adapters or adaptation, which basically creates two matrices called as update matrices. And when the new data is given to fine tune, the update matrices are only fine tuned. So the rest of the model parameters, say for an example, if you take the GPT 6 billion model, all the 6 billion parameters that is already available is frozen, meaning it will not be changing. Only this update matrix that is created by the low ranking adaptation configuration, only that will change. So the size of the new model will be very, very less. So I'll be showing you a couple of examples also that I have taken from the Transformers library for you guys to understand. Not Transformers library, from PEFT library. Sorry about that. Next is prefix tuning. So in case of prefix tuning, what happens is the model itself is modified in such a way that additional parameters are added to the model, and only the additional parameters are going to be fine-tuned, and these additional parameters are prefixed in all the layers of the model. So that is called as prefix tuning. I am not going to dive deep into this visualization of what exactly happens. You guys also don't need to really understand, but if you are planning to develop, go in detail into PyTorch and in detail into Transformers and PEFT, then I would suggest that take a look at their documentation. But at this level where I'm introducing, I would suggest that all you need to know is that there is something called as prefix tuning. And when you are going to use PEFT library, there will be an option to use this prefix tuning. So that is one of the point I wanted to highlight here. So prefix tuning stores 10x fewer, 1000x fewer parameters. So this is the key point I wanted to highlight. And prompt tuning is also very similar to prefix tuning, but in case of prompt tuning, what happens is each of the task, the prompt of each of the task is created as a separate prefix, and it gets added on top of the model. So let me borrow it from the library itself, just a minute. So if you come to Hugging Face Hub, you can just click on PEFT under the docs, that is documentation. And if you actually go to the concepts, if you go to the prompting conceptual guide, and if you scroll down, they talk about all these things. So they talk about prefix tuning and prompt tuning, etc. And inside the prompt tuning, you can see that each of the task is maintained as individual parameters. So 20k parameters for each of the task. So if it is going to be task A, 20k parameters, task B, another 20k, and all these parameters, additional parameters, are added on top of the existing model. So it's a very good way of explanation that they have given. And this prompt tuning was first of all developed for text classification task on T5 model. What we are going to do is, so basically we have seen what are the various ways you can use PEFT and prompt tuning, how to work with these things. What actually happens in case of PEFT is there is a configuration file that you create, and you send that configuration file to the model, and the configuration file decides which part of the model needs to be trained, and then you train that model. So you will see that in action in a couple of minutes. So let us go to the browser. This example that I'm taking is from the library only. And what I'm going to do is, before we start, I'm going to stop this disconnect and delete the runtime so that I can use the runtime in my PFT area. So let me go here and let me go to manage sessions. Sorry about that. Let me go to this and let me actually change the runtime, and I will give GPU accelerator to this. Okay, so in case of free collab environment, you can have only one GPU instance. So that is why I'm swapping it here and there. And you can also do this. So there is nothing stopping you guys. So this particular Jupyter notebook that I'm using here, as well as this particular Jupyter notebook, I'll be sharing with you guys over the GitHub repo, and the link also I'll be sharing it to you in the description below of this YouTube video. Okay, so here again I'm starting with all the necessary libraries, and the difference here is that you see all these config files: get PEFT config, get PEFT model, get PEFT model state dictionary, tuning config. These are the various functions and methods that are going to change the way how you are going to train the model. So what is a regular training process? Okay, in the regular training process, you first of all start importing the tokenizer. You will start importing the model. So the tokenizer and the model you will import, and then you will have a set of data, and you will fix the training configuration. So there is something called as trainer inside transformers. So if you have not taken a look into that, I would suggest you guys to take a look into these sets of videos where I introduce data sets, the idea of agents, the transformers, etc. in this series of videos. Take a look at that, you will get an idea. And once you are able to train it, so once you train it, once you set the training configuration, you will give the training data set, and it will get trained. But as I already told, the regular training process is going to train all the parameters in the model, meaning the new information or the new dataset information will pass through all the parameters inside the model. So it will spread through the entire model, and the entire model will learn. In case of PEFT, we are going to just keep the learning to a part of the model. So this is the difference. I am not actually diving deep into the actual algorithms that is getting used there. It's a little more complicated. I should say complex. It's not complicated. So you can actually learn it. It's not that difficult also. Once you put some effort and time, you will be able to master that also. Coming to the discussion at hand. So here there are a couple of methods that you are going to use, and here you can see. Okay, first of all, I'm going to load the dataset. I'm going to go a little fast. Okay, don't worry about that whether you are able to understanding or not. First and foremost, get the overview, and then once you get an overview, once you understand, okay, step 1, step 2, step 3, step 4, then you can actually dive into each of the steps and understand it better. So when I was preparing this video, I was also going through the same process. Especially for Accelerate and PEFT, getting the overview is a little bit difficult. So I hope that this video actually helps you to get the overview. I am loading the dataset, okay, and this actually processes the dataset. And as I come down, I am loading the tokenizer, and I am going to process the dataset with the tokenizer and tokenize the dataset and encode it. Okay, so this is all the process I am doing, and this is where the entire dataset gets processed. I'm going to create a data loader. So this data loader is part of Torch library, that is PyTorch library. And here comes the interesting part. So this prefix tuning config. So this is where I'm going to create the task type, what kind of task I'm going to use, what is the inference mode, I'm going to say it as false, and what is the number of virtual tokens. So I'm going to use prefix tuning. And once I use this prefix tuning, I can actually pull the model down. So I'm pulling the model, and then I'm going to send this model into the get PEFT model. So once I send this into the get PEFT model method or function, the model and the PEFT config, then I get a different trainable parameter. So you see that the number of parameters that is trainable is 983k. while the actual parameter is 738 million parameters, 738.6 million parameters. So out of that, only 983k parameters I'm going to fine tune. So this is what I was talking about. And once the model gets fine tuned, so I'm going to give a classification process for this. So all this process happens. I am not going to go into that. I would come back to it. So give it a moment. So I want to show you the actual process. So once the model gets trained, and once I push it to the, after the model gets trained, I will push it to the Hugging Face Hub, or I will take the model. And you see the model size is actually very, very less. So the entire model size is less than 3.4 MB. Can you believe it? So after I do the fine tuning, the new model size is less than 4 MB, that is 3.93. If you click on this and if you go to the Hugging Face Hub, this particular repo, I will make it public so you guys can take a look at it. And if you go and look at the file, and so immediately you can see that the config JSON file, you can see that here. And also, just a minute. So here you see the adapter model bin. So this is the new model that has been created, or it's not a new model, it's the new part that has been created. So you guys can understand what is going on here. For a new task, so let us go back, let us go to the, let us go here. So for a new task, say for an example, if you want to create a summarization task or a translation task, that task becomes a new kind of a part model. And the part model, that is adapter model, can then be attached to the main model and it can work together. So it's kind of a functions that we use in regular Python or regular programming, but these functions are created using large language models. And also you saw that you are not writing those functions. So assume that you want to, here they have given a very good example. So here I give a sentence like this, that name Starbucks, type coffee shop, and this is table to text. So this is a table that I am reading it in, and the outcomes, the actual answer, Starbucks serves coffee. So this is kind of a conversion from table data to text data. I can create a function for this. I can write a Python function. I can get the data from the table, convert it using various Python primitives or classes, or how to say, inbuilt functions, string functions, and I can write it. But I assume that I don't know anything about Python functions or programming, and I want to create this function. So all you need to do is understand how PEFT and transformer model works, and then you are set. And moreover, this entire process that I'm talking about will be automated. So most of the time, the entire process that you see here will not be visible to you. So you will be giving the data, you will be asking for the task, and the model will get fine-tuned and your new model will get created. So you must be right now thinking, so I have seen such a kind of fine-tuning somewhere. So if you have already fine-tuned the ChatGPT model, in the beginning when ChatGPT and OpenAI came up, so there was a process of fine-tuning the OpenAI model. So even in that OpenAI model fine-tuning, right, the entire model had to be fine-tuned, and part of that model was shared with you guys. Now what I'm trying to say is that you don't need to have the entire 6 billion or 7 billion models parameter fine-tuned. Only part of it you are going to fine-tune. So why am I saying this? I will again show it to you. The actual T5 large. So if you go to T5 large, if you go to Google Flan T5 large, that is the actual model. If you go to that, the model size, if you go to the files inside that particular repo, you'll see the model size is in 3.13 GB. So the base model size is 3.13 GB, but the one that you fine tune is less than 3 MB, that is less than 4 MB. So this is what I was trying to say. And the same way, there is another one way of prompt tuning. Prefix tuning and prompt tuning are very similar, but the way the data is getting created is different. And we already saw Lora is again a configuration. So let me go to the browser again, and let me show you the Lora configuration. Let me go down. So here we saw, so Lora configuration I have not discussed here, but I have discussed the prompt tuning configuration, that is prompt tuning init, and prefix tuning. So Lora configuration I have not discussed in this particular video. You can actually take a look at the Lora configuration using the examples. I would actually request you guys to do a practice about that. Most of the things are already available in this particular library itself. All you need to do is go to the respective tasks, and you can start practicing it directly. So with that said, let us get back to the presentation. We have discussed two important points today in this video, that is how to load huge models into your own resources, which may not be that much huge. So how to do that? We spoke about it using Accelerate library, and then we spoke about a different way of fine-tuning or training your model called as parameter efficient fine-tuning. And we went into the details of various configurations like Lora config and the prefix tuning, prompt tuning, and the examples of how to create the model ready for fine-tuning. So we went through that process also. And we understood that each and every task can be fine-tuned separately, and you can have separate models for that. So with all these things, I believe that you have learned a lot in this particular discussion. Do leave a like and share it with others. Subscribe to my channel for further updates on not just on large language models, but on the entire Python open source ecosystem. With that said, I would like to close this video with 4 words, that is practice, practice, explore, explore. See you guys. Have a great time.